Okay, I think we are now live. So good morning, everyone. Thanks for joining. There'll be 4 workshops on the Verifiable AI Hackathon, which is being done with Google Cloud and our community partners, Blockchain at Berkeley and Dora Hacks. Today is going to be a 1-hour session where we'll cover 2 of the 4 tracks. We'll look at social AI agents, and then we'll cover RAG knowledge. So I'm Dinesh. I'm the technical product lead at Flare, and I'm joined today by Horia, research scientist at Flare. So I'm going to start by going through some of the some slides, basically describing why social AI agents are important and how they can help us, how we can use verifiability to create better social AI agents. So I'm just going to share my screen. So I think you can see my slides at the moment. So this is part of the FlareX Google Cloud Hackathon. There'll be a total prize pool of 100,000, and the goal is to build verifiable AI agents with Flare and Google Cloud. There are 4 tracks, as I mentioned. Today we'll be looking at social AI agents, and we'll be looking at RAG knowledge. And if you haven't registered yet, you can always go to hackathon.flare.network and get yourself registered. So this is the structure of the first workshop. We'll look at what are social AI agents, why do they need to be verifiable, and then we'll see how we can create social AI agents using Flare AI Kit. And I'll go through some of the templates that we have built for this and do a little live demonstration. So let's start with what are social AI agents. At its core, social AI agents basically generate human-like content, and they interact autonomously on social media. So a couple of key features: they're aware of the context. So if you're talking with a social AI agent, they understand that you're having a conversation with another person. Maybe they understand some characteristics about that particular person, and they're able to interact with them. So it can engage with this other person in real time. And they do this autonomously. So they follow maybe a set of predefined protocols or like rules within which they operate. But outside of that, they can basically do whatever they want. And this is made possible through large language models like Gemini 2.0, which is what we will look at in this particular workshop. And the interface could be through any social media platform. It could be through X, it could be a Discord bot, could be on Telegram. And you can combine these social AI agents with things like RAGs, which Horia will describe in the next talk, to make them smarter and give them more functionality. Why do they need to be verifiable? So we have seen a bunch of social AI agents, on places like X, Discord, and Telegram. And the problem that we have today is that we don't know who's actually running them, right? There could be a person behind the scenes who is controlling the account, who has, admin keys. They can pull the account whenever they want. And they could also, craft messages for specific things. So we don't know that. There is no proof that we have that there's an actual human being, the code is actually running autonomously, right? And this is just one example I pulled up from X, but there's many such cases, right? So at its core, we don't have a proof that you're actually interacting with something autonomous. You're actually interacting with a social AI agent running a particular model. And that's what we want to change at this hackathon. So there are mainly 5 steps to creating a social AI agent. First, you need to conceptualize and define like your objectives and target audience. So is the social AI agent going to be focused on X users? And then what will be the purpose? Is the AI agent going to focus on, maybe it's going to focus on Flare. It's going to focus on developing applications on Flare, so on and so forth. So you need to define what your objective is with this particular agent. Next, you need to collect some data, right? Your data could be things like training data sets from a person's tweets. So I'll give an example in the next couple of slides, looking at how you can fine tune a specific model using data. You then want to pre-process this data, so basically transform it into a way that an LLM can actually train upon that. And then you want to do the fine tuning itself. So fine tuning is the process where you adjust some weights and biases within the LLM to make it more suited to a specific task. And lastly, we're going to deploy this agent within a trusted execution environment. And this is what will give us that final element that's been missing. That is the verifiability, that we're actually running the code that we claim to run, and that there is no human involved behind the scenes of like an X account or a Telegram bot or something like that. So let's start by introducing Flare AI Kit. At its core, Flare AI Kit is composed of 4 different parts, and they're all working together towards one goal. And the goal is to build like a developer-friendly and security-first SDK for blockchain AI agents. And the way that it's doing that is through something called trusted execution environments. And trusted execution environments are basically secure areas of modern CPUs, which isolate code execution, which allows them to basically run a particular piece of code and then attest that that particular piece of code was run only within that environment. So for example, you could like create private keys, and that would only exist within the trusted execution environment, and you can prove that that is actually the case. So right now we have 4 templates. Today we'll be talking about the first 2, that is Flare AI Social and Flare AI RAG. For my talk, I look at Flare AI Social. And the structure of the repo is basically looks something like the image you see on the right. It's very modular, so you can like pick and choose, which part you want to interact with. And if you don't want some part, you can just ignore it or delete it. It doesn't really matter. But there are a bunch of services that we have. So first is the AI service, which basically natively plugs into Gemini, especially Gemini 2.0. And we also have an open router integration, which is required for some of the other tracks where you need to do, let's say, some sort of consensus across different LLMs. We then have an API endpoint. This is using fast API and allows you to like expose particular endpoints for front-end communication. So if your front end, for example, is X, or your front end is going to be Telegram, you can plug your front-end code into this API and use it there. We also have attestations support. So we support VTPM attestations generated by Google Cloud Confidential Computing. And this is all abstracted away. So you can very simply, just by querying one function, get a remote attestation from your trusted execution environment. And then we have something that is more specific to Flare AI Social. We have a prompt library. And this prompt library basically is a set of prompts that you will be using for interactions with the end user of the social AI agent. So let's get into some of the details. So let's start with step 1, where here we're going to generate a training data set. So data set can be anything with a mapping of input text to output. So on the right, we have an example of a training data set where we effectively just take a set of numbers and we shift them by 1. So if the number is 1, the output would be 2. If the number is 22, the output would be 23. And you can do this with anything. So I've given some examples over here. This could be forum posts and moderator comments. It could be tweets and replies of Hugo Fillion. Hugo Fillion is the CEO of Flare and co-founder as well. And it could also be things like, as we show here, numbers and the next number sequence. Now, we do recommend that you keep a minimum data set size of about 20. And ideally, you would use much larger data sets, which would be somewhere about 100, because we're going to use these to fine-tune Gemini itself. And if you're more interested in digging into it, you can look at this link over here. Under source, trainingdataset.json defines this training dataset. Next, we want to start fine-tuning our model. So there are a couple of ways that we can fine-tune it. The first is supervised fine-tuning. So the idea here is that you actually retrain the base model on your labeled dataset, and this will change the weights and biases within the model. And this is generally good for performing like more complex tasks, and if you have like a nice training data set that you can use. The second method is using prompting. So here, this is probably more familiar, I guess, to most people. Here you basically have to design a prompt that conveys the task that you want and how you want the output to be. So what I recommend personally is you use both of these techniques, but use them for different scenarios. So first, when you're creating a new model and you want to play with it and get started quickly, you want to start with prompting, right? And then once you have built up this knowledge and this prompt data set, then you can move into supervised fine-tuning. So let's get into the supervised fine-tuning itself. We're going to use a foundational model, Gemini 1.5 Flash over here, and we're going to train a new model based on this data set of tweets from Hugo Fillion. And this new model is going to be called Agent Hugo Fillion. And if you look at the image on the right over here, this is effectively showing the loss parameter versus the number of training epochs. So what you would expect is that as you train the model for longer, basically the loss is going to keep dropping. And at some point, you will effectively get a convergence, and the loss will more or less be sitting near 0. And that means you've effectively trained it on this particular data set. Now, there are a couple of caveats over there. There are things like overtraining, overfitting, and so on. And this is described in more detail in the code, and we'll get into that when we actually look at the database itself and the code. The next technique is prompting. And within prompting, there are a couple of different ways that you can do it. There's zero-shot prompting, where you just directly instruct the model to perform a task, but you don't give any examples for it. There's few-shot, basically the same thing as zero-shot, but with some examples. And then last is chain of thought. So this is basically where you don't give the model examples necessarily, but you tell it how to think about a specific problem, right? And we look at examples of them in the next couple of slides. So this is what a zero-shot prompt looks like. So it basically, in this case, you're telling the model that you're Hugo Hillian, you have a good amount of blockchain knowledge, you're analytical, you know about Flare, you know about XRP, you know about Flare's protocols like FTSO, FTC, and you tell it how it wants to behave. So in this case, it's confident, it's conversational, and it's analytical. So this is an example of a zero-shot prompt because we did not give it any actual examples to deal with. If we go to a few-shot prompt, we basically have the same initial prompt, so that's the section at the top, but we add in some examples as well. So we tell it, okay, if I was given this input, this is how I would respond to it. And generally speaking, few-shot prompts will perform a little bit better than zero-shot prompts, because zero-shot prompts tend to be a little bit, long-winded sometimes because they don't have that context of how they should particularly respond in each scenario. And lastly is chain of thought. Here, basically, you're going through the way the model should think about the problem. So you can tell it like, okay, if I get some input, first I want to categorize it. Then I want to understand what is the context, and then construct some kind of framework to response. And you can give it some examples of how you would think. So for example, if I was giving the model the input, something like this with all this talk of the Dogecoin standard. So this is a tweet. First, I want to tell it, okay, the category is ecosystem development and market dynamics. There's a context, users curious about strategic decisions, and there's a framework for understanding that particular context. And the style and response that it needs to make will be derived from this chain of thought that the model is following. And these examples are all present in code, and you can follow the links here at the bottom to go to that particular section. One thing I would recommend is that if you're building with Flare AI Kit and you're using Gemini, I would recommend rapidly prototyping with AI Studio. The link is pretty simple. It's aistudio.google.com. And you can adjust a lot of parameters over here to train your model, right? Like you can adjust the temperature, grounding, you can tell it to give structured outputs, and you can also support like code execution in there. And something that's quite interesting is about Gemini has really good support for multimodality, which is not just text-based inputs, but also inputs like, let's say, voice or video or things like that. So I would say for the hackathon, a great area to experiment is going to be text-based and not going beyond text-based inputs, doing like audio inputs or video inputs and playing with that. Lastly, we're going to deploy it on a confidential space trusted execution environment. Now, confidential space is like a subsection of confidential computing. And confidential space itself, it's like a minimal trusted compute base or minimal TCB operating system for trusted execution environments. And what it does is it basically runs like a single Docker container, and it has a set of boot measurements with no remote access or logging, right? And the single Docker container will basically have like all of your code logic embedded within it. And when you generate a remote attestation, it will basically attest over that particular container. So the hash of that particular container image will be in the remote attestation. So when you see a remote attestation from a confidential space environment, you can be like, okay, this environment has this particular Docker container running on it with this configuration, and there's nothing else that can be done about it. Like no one can remotely access it. No one has access to the logs that are generated from this system. And the way you can prove that is basically because of the underlying TE hardware, which is supported, confidential space supports both AMD SEV and Intel TDX. And for the hackathon, you're free to use whichever one you see fit. We have abstracted away remote attestations with our VTPM logic that I described earlier. For testing purposes, it's actually a little bit easier to have logging. So we would recommend you use the debug images for testing. And when you're ready for final production, then you go to the production level image. And in this workshop, we'll actually go through what this looks like. Okay, we also want people to be responsible. Like here, I gave the example of training a data set with tweets from Hugo. But within the hackathon, we need to be very careful with how this is actually used. And basically, all AI agents must specify that they are actually agents and that they're non-human. And also, impersonation is basically strictly prohibited. And if you do try and impersonate someone during the process of this hackathon, we may be forced to terminate your instance and also potentially suspend you from the hackathon. So please don't do that. If you have any doubts about this, you can always, of course, reach out to us. But a good general framework for thinking about these questions is the Responsible AI Principles, which is laid out by Google. And it's over here in the link, and you can go and read through it and understand sort of how to approach these problems, because AI is a very powerful tool, but it needs to be used carefully in a responsible manner. Okay, now I'm at my last slide. The hackathon onboarding is going to start on March 6th. You can visit the link dev.flare.network/hackathon/onboarding to get started. Feel free to reach out to us on Telegram for support and to check out the different template repos that we have. So what I'm going to start now is I am going to start a test deployment of Flare AI Social. So I'm going to navigate to Flare AI Social repo. What you want to do is want to click use this template, create a new repository. And what I'm going to do is in my personal account, I'm just going to basically create this repository. So I'm going to make it public over here because we need to pull the images from the GitHub Actions build into confidential space. This takes a few seconds. Okay, now it's done. Now I already have this image locally. So what I'm going to do is I'm going to navigate into it. This is what it looks like. So I have a couple of things over here. So what I'll do is I'll actually go through like the README and walk through like the step-by-step process of what you need to get started with using this. So let's start by basically installing our dependencies. So you can just see this command over here. The backend dependencies are managed using UV because our backend is written in Python. So you can just copy this command and just run this in your shell. And we've already run it once, so we have all our dependencies. When you want to train a new model, what you can do is you can go to source data and training data.json, enter all your data over here, and you can then enter the command UV run start tuning, and that will basically tune a new model over this particular data set. And the image I showed before, it will output that image as well. So you can observe whether the model has successfully been trained, or maybe there's some optimization and parameters remaining. And to optimize your parameters, you can look at the example environment. So the example environment has a couple of parameters for fine tuning, things like the base model, the number of epochs you want to tune it for, the batch size, and the learning rate. We have set some pretty sane defaults over here, but depending on the size of your training data set and how complex it is, you may need to tweak these a little bit. Next, we're going to build this locally, and we're going to build it using Docker. So again, just copy the command from here and paste it into your terminal. And what this is going to do is it's going to build a local Docker image with this new model that we have tuned. And it's also going to build a front-end UI for it so we can interact with it locally. So what this front-end UI is basically doing, if we look at like the Docker file for the project, we start off by building like the front end. This is a multi-stage build. We're then going to build the backend, which is in Python, and then we're going to combine the two together. We're going to put a Nginx proxy at the front, and we're going to use supervisor D to run both the front end and the back end within the same Docker image. Now you'll see this label parameter over here. This is something that's required by confidential space. Basically, it allows you as the Docker creator or the container creator to override certain environment variables. In this case, we're overriding environment variables like API keys, the model name that we have tuned, and also whether we want to simulate a remote attestation or not. For local development, we recommend simulating the attestation, but when you're working on confidential space, then of course you want to use like the full attestation itself. So it looks like our Docker build is now complete. We can now try and run this. So let's just copy the next command and run that. So when we see an output like UVcorn is running at 0000, that means we know that this has been done successfully. So that generally takes a couple of seconds, but once it's ready, what you can then do is you can navigate to your local host and you can observe the chat UI. So, okay, it looks like it's ready over here. So I'm going to open a browser window, going to navigate to localhost at port 80. And here what we see is a locally running instance of the front end, which is connected to the tuned model at the back end. And I can use this front end, to like chat with Agent Pugo-Hillian. I can ask agent questions. This is a good way to fine tune and make sure that your model is working in a way that you would expect it to work. So now that we have like a good basis set up, what we can proceed with is the next steps. You can also build this like manually, so you can do the back end and the front end separately. I won't cover this in the talk. The instructions are, I think, pretty clear. But what we're going to do is we're going to deploy this on a trusted execution environment in Google Cloud, right? So for this, first you need access to Verifiable AI Hackathon. This is a specific development environment just for the hackathon participants. And when you're in this environment, you'll basically see something like this. You're working in Verifiable AI Hackathon. And you will be given access to this on March 6th, which will basically be like one day before the hackathon. And when you run your code, you can run it basically within this environment. And you won't have to pay for things like Gemini or compute and so on. That'll all be handled by the project itself. So you also will need a Gemini API key. So you can just go to this link over here in the README, and you can get yourself a Gemini API key just by clicking on Create API Key. And once you have set those up, you will also need the G-Cloud CLI. I won't go over it in this talk because it depends heavily on the platform that you're currently using, but Google has a very clear set of instructions on how you can install the G-Cloud CLI. So let's start with actually configuring it. So first you want to update your .env file, and you want to add your image reference and your instance name. So the image reference is where you're sourcing the image from. In this particular case, we're going to source the image from Flare Foundation, Flare AI Social. When you clone the repo and you use the template, this location will change to whatever repo you have cloned it to. And the next thing you want to add is your instance name. So for this, you just want to add a project name and a team name. Here, I'll just call it something like Dinesh Social, right? Just give it a simple name. And next, you want to load these environment variables into your current shell. So let me go ahead and do that. Now, this does require the source command, and you may have this issue, and we tested it out on Windows, that you may not have the source command in your current shell. For doing this, you just get git bash, and git bash supports sourcing. And the reason we need to source is because the final command that we will use to deploy on the TE, it actually uses some variables that are injected by the .env file. And lastly, all you need to do is basically copy this command over here and paste it. It's a pretty long command. And if anytime you feel a little bit confused as to, what is this command? What does it mean exactly? What you can do is you can go to dev.flare.network onboarding and go to the cookbook. And here we have the full command and a breakdown as well, like what each individual line within that command does. So you can understand it and maybe make some tweaks as well. So for today's presentation, I'll only look at AMD Sev. But if you are interested in deploying on Intel TDX, we have instructions for them on the Flare Developer Hub as well. So let's now run this command. And if everything works correctly, we will have an instance created on Google Cloud running in a trusted execution environment with the name Dinesh Social. So it takes a few seconds generally to deploy. But once we deploy it, we're going to look at the logs of the system because, again, this is using a debug image. And we're going to see, was the deployment successful or not? OK, so it looks like the deployment was successful. We got our name, Social Dinesh. And we also have some internal and external IPs for this. So let's go to the hackathon homepage. This is the Verifiable AI Hackathon GCP space. Go to Compute Engine. And then select VM instances. And within VM instances, there'll be a bunch of them. So make sure you select the right one. The one we deployed was Social Dinesh. So let's click on that. And you'll see two types of logs over here. So the first one logs to something called cloud logging. And the second one is a serial port log, so the console. So let's click on the second one. And we can see that, OK, it's generated a bunch of machine logs. And you don't have to understand like all the details of this machine logs. But basically what it's doing is it's booting up the TE, and it's running a set of integrity checks on the system. And this can take a couple of minutes. Right. So when it's taking, basically after it's done, like doing all these internal checks, it will then try and load your Docker container. And once it loads your Docker container, you'll basically see the same image, the same message over there, which is 0000, and Uvicorn is running at that port. So let's see if that happens. And there we go. So we can see that Uvicorn is running on port 0000. So what should happen now is we should be able to navigate to the external IP of this instance and get exactly the same chat interface that we saw when we were doing the local build for this. So if you go back to your instance, scroll down, copy the external IP address, and then navigate to it. And there we go. So this instance, even though it looks exactly the same as the Docker one, is actually being served from the trusted execution environment itself, which basically means that we did a deploy of our agent on the trusted execution environment, and now we can interact with it. And this interface could be anything. It could be, a Telegram front end, an X front end, whatever you want to do. Okay, I think that basically covers what I wanted to talk about on the social AI agent side. So next, the talk we can hear is basically from Horia. And Horia, feel free to jump in.
Okay, I'm back on stage. Give me a second, let me share my screen. All right. So hopefully everyone can see this. I'll do the second part of the workshop, which will cover a different track. So today we're covering two of the four tracks, and the one that I'll focus now is on retrieval augmented generated knowledge, or as we call it, RAGs. So the idea here is that we want to develop systems that deliver accurate and then context-aware answers. And to do this, we'll build one of these RAG systems. So we have a RAG kit, similar. The code is somewhat similar to all the other four templates, and you can access it at Flare Foundation Flare AI RAG. And for the talk today, I'll tell you a bit about what RAG systems are, why we care about them, and how we can use them. I'll describe the architecture of the Flare AI RAG template. As a simple overview, the kit is built by is composed of three components. We have a router, retriever, and a responder, which all rely on Gemini. We have a very similar chat user interface to what Dinesh already showed us for the Flare AI social template. And then I'll walk you through the steps of how you can get started with the template and give you some hackathon ideas and the next steps. So why do we care about Flare AI? Why do we care about RAG systems? I'm sure that I'm not the only one who's tried at some point to just put some very large document in an LLM and ask for a very specific information out of this document. And more often than not, this leads to hallucinations. So typically with RAG systems, you are in a situation where you have a very large database, which you can't really use as a context, or if you do, it's very likely that you'll get hallucinations. And as a result, you need some way of fetching only the relevant data sources and use those as context for the LLM. So all these RAG systems contain what we call a retriever, which performs this search and tries to fetch the documents that are relevant for the query from some external database. Okay, and for the template I mentioned earlier, we build this with three components. The first one is the router. So a user comes in with some specific query. The router relies on some LLM, which here is set by default to one of the Gemini models. And this router will act as a simple filter for unclear queries or queries that are not related to the Flare blockchain, to Flare networks or blockchains in general. So if that's the case, then the router will simply send back the query and ask for some clarification. If this query is well defined, then it passes to the next step, which is the retriever, and is the core part of the RAG system. So the retriever needs to be able to get the contextually relevant documents from some specific database. And the way we do this is by using embeddings. So if you focus on this diagram at the bottom, the embedding basically takes some input documents, passes it to some neural network or some pretty complicated model in general, and gives us as output a vector. This is here just a one-dimensional case, but it can be in general a very high-dimensional representation. And all these vectors are then stored in what's called a vector database. So once we generate such a vector database, every new query from a user needs to pass through the same pipeline. So it is also going through this embedding model. We get a new vector for the new query. And now we have a set of vectors that we can compare with some methods like cosine similarity. So we look for vectors that that have a similar angle in a vector space. Okay. You can see more details about how this is implemented in the Play AI RAG retriever, but I'll share some more details in a moment. So for the template, we use Gemini's text embedding model, and all these embeddings need then to be stored in a vector database. Google offers some cloud alternatives. For the template, we went with self-hosting vector database, and we're using Quadrant for this. There's other alternatives if people want to explore and experiment. But one of the requirements is that when running in confidential space, everything needs to run within the same Docker container. So people need to be a bit careful and try to make sure that you don't need a separate Docker image when running your vector database. So to set up the retriever, I promised earlier just to go over the to have a very high level idea of the code. We essentially initialize the embedding client, which is a way to connect to Google and use the text embedding model of Gemini. Then we need to generate what is called a Quadrant collection, which is where all the embeddings will be stored. And once this is done, then we can finally look through all the vectors that are stored in our collection and do a similarity search between our new query and the new and the already stored vectors in the database. So the final component of the RAG is the responder, which is another LLM with a slightly different system instruction, where we use the retrieved documents from the previous part, the retriever, as additional context to provide a better answer. So as you see in the diagram, the retriever will search through the vector database, will pick some relevant documents, and then all these documents are passed to the responder, which provides this as additional context to the Gemini model. So we have the same chat user interface as before. It's built in React, and I think I have it running. Let me try to see if I can switch to this. One moment. Okay, so yeah, I'm basically running this locally on my computer. The instructions are very similar to what you've seen from Dinesh, and in fact, we try to have all the AI kit templates share quite a few features. The UI is one of them, but then the setting up the Gemini clients is also very similar in all throughout all the templates. And this Flare AI RAG template now has a database, which is essentially a CSV file of all the information that's available on the Flare Developer Hub. So I can ask what's the average block time on Flare. It's going to tell me that it's roughly about 1.8 seconds. But one feature that is quite nice and we'd like for this RAG to have is to provide the sources. So document 0 overview here is one of the documents that we used as input for the RAG. Okay, let me just go back now to my slides. Okay. So getting started with the Flare AI RAG, the first thing, and possibly this is quite underrated, is is preparing the data and pre-processing it. I'll mention this more on the next slide, but I already showed you that what we prepared for the hackathon participants is the Flare Developer Hub in a CSV file, and this is available in this link in the repository. For the next steps, if you want to directly run the template, you'll need to simply go to this input parameters, where you can configure the LLM model for the router. So this is one of the Gemini models. Then you can pick an embedding model. There's 2 embedding models that you can use for Gemini. But of course, you're not forced to use this. So we experimented earlier with some Hugging Face open source models, which you can get with a sentence transformer. But this usually means that you'll need to download the whole model. So your Docker image will be quite a lot larger. And then the final step is also choosing a model for the responder. The README instructions are pretty detailed on how you can build and run, but for all the 4 templates, they are rather similar. The whole repository is quite modular, as Dinesh also pointed out. So if you want to add additional components or you want to change completely some components, then this should be quite straightforward. So some ideas for what people could try for the hackathon. So the data pre-processing is something that, as I mentioned, is often overviewed. So you can look at other data sources like the Flare Foundation GitHub or the Flare website, blog posts, white papers. If people are interested, we can also provide Flare time series Oracle data and FDC data, depending on what use cases people might come up with. Segmentation of large documents is definitely needed. So for the embedding, we're using the generative AI package from Google, and this, if I remember correctly, sets a hard limit of around 10 kilobytes. So the one alternative is to use the Gen AI, the slightly newer version, but that it doesn't necessarily mean that that if you have a larger limit, this will give you better results. So keep this in mind. Okay, and of course, one can add or make use of metadata. So we only use for the template, we only use a simple semantic search with this cosine similarity. But you can integrate better search techniques. You can use keywords. You can improve the efficiency of the data retrieval with different embeddings and search methods, and of course, providing a better context for the retrieval. So pre-processing of the initial query can also improve the RAG pipeline. So we're excited to see what use case people can come up with. The RAG system can be very powerful, not only for the social track, if anyone is thinking of combining, but the DeFi or any other AI use cases are usually quite useful for it. The responsible AI practices, I think Dinesh already covered those, so I won't bother you again with those. But for the next steps, get ready for the onboarding, and don't hesitate to reach out if you have any questions on the Telegram group. All right. I see there's some question. Dinesh, you're back.
Okay. Yep. Thanks. Thank you, Horia, for that. There's a question in the chat. Why do we use a TEE? Why don't we just use a normal environment? So TEEs effectively allow you to prove what container was used. And if you can see what container was used, you know what code was executed within that particular container. So in tomorrow's live stream, we'll actually show an example of how that can be integrated into your development workflow. We'll use the attestation module to do that. I can give you a little sneak peek of what that looks like. So I'm just going to share my screen again. So we have this VTPM attestation component, and this is modular, and it's present across all of the 4 templates that we have. And basically, you can call the method getToken, and you have to supply it with like a set of nonces and an audience and a token type. The default is set to OIDC, which is an OpenID Connect token. And when you do this, it will give you something that looks a bit like this. It's like a long string of what looks like gibberish. But what you can do is you can take this string and you can go to a website called jwt.io, and you can then paste the string into jwt.io. And what you'll be able to see over here is, number one, that this was running on confidential space, and it was using AMD SEV processor. And it'll give you information about the container itself. So in this case, you can see that this was a container that I created from my GitHub account. And the name of the container is test confidential. And you have a digest, a SHA-256 hash of that container itself. So I can say that this particular container with this code base is running on this trusted execution environment. And I can also see things like, what all environments I have, what were the environment variables overridden over here, basically which zone is it running in. All this metadata about the system is basically made aware to me. So when I have this remote attestation, I can then use this in multiple ways. I can, for example, use it to create a TLS channel, right? So for example, if you might have noticed it, the front ends that we had, they did not have the little lock icon on there. That's because they're not using HTTPS. But what you can do is you can actually take the remote attestation report and use that to create a secure TLS channel so that you can communicate with the front end in an encrypted manner. You can also showcase these raw attestation reports to the end user themselves, and the end user can then go and verify them. And we have a verifier as well. So there's 2 main things here. There's VTPM attestation.py, which allows you to create attestations. And then we have VTPM validation.py, which allows you to verify attestations and match that and ensure that they meet like a specific criteria that you have predefined. So hopefully that answers your question. Okay, if there aren't any more questions, yeah, thanks everyone for joining. Tomorrow we'll be doing the next two workshops. That is going to be AI x DeFi, how you can make DeFi better using AI. And we look at consensus learning, so looking at basically multiple LLMs and trying to aggregate the output across all of them. So thanks a lot, Horia, and see you guys.
Thank you. See you.